Cowboy Joe here with a recapitulation of section 14.30 on wave behavior. And your goal by the end of this video lecture will be to relate a wave speed to the medium in which the wave travels. Apply the principle of superposition to the phenomena of interference and describe how waves are reflected and refracted at boundaries between media. Well, the speed of a mechanical wave depends only on the properties of the medium. For example, water waves depend on the depth of the water. The deeper the water wave is, the faster the wave will travel. In air, we could talk about sound waves, how you're hearing my voice. Well, the warmer the temperature, the faster the wave will travel. In slinkies, it depends on the tension of the slinky and the mass per unit length. So for all these examples, again, the speed of the mechanical wave depends only on the properties of the medium, not the frequency, wavelength, or amplitude. If I were to change the frequency, I could get real low or I could get real high. That would be a change in frequency. The amplitude change is how loud it is. So if I yelled, it would be a lot louder. If I talk soft, it would be softer, and that would change the amplitude. But these guys do not change the speed of the wave through the medium. The wave that strikes a boundary is called the incident wave. The wave that comes back is called the reflected wave. Notice when this wave strikes the boundary, it is inverted, meaning it's coming on the bottom of the line. The wave pulse actually returns on the bottom. If the wall is not rigid, it will return upright. So the principle of superposition takes a couple of these waves and heads them towards each other and causes interference. Well, this principle states that the displacement of a medium caused by two or more waves is the algebraic sum of the displacements caused by the individual waves, which is what we call interference. That's what results when two waves interfere. Imagine wave A headed towards wave B. Well, what happens in the middle? They add their amplitudes together. This is called constructive interference. And after they pass through, they go back to normal, the normal amplitude that they hit each other at. They actually will travel right through each other. An example of constructive interference is the medical process called lithotripsy. Lithotripsy sends waves in around your body to shatter a bladder stone or a kidney stone, but the little waves that they send through the body don't bother you, and when they all meet together in the middle, the amplitudes are increased to the point where they're able to shatter the stone and you could pass it naturally. Destructive interference is the opposite, where they're subtracting their amplitudes. They're canceling out each other. So if wave A is traveling towards wave B on opposite sides of this line, the amplitudes will actually, if they're exactly the same size, they will eliminate each other right at the point where they meet, and then again continue past each other. They travel right through each other. So this is an example of destructive interference. An example in real life of destructive interference would be like jet engines. Their engine is so loud that it actually will cause hearing damage to the passengers. So they created a noise reducer that will take away some of that sound, making it a lot more bearable. Now we could look at another scenario where maybe you tied a rope to a doorknob and you started spinning it, maybe even tied it to a drill. If you turned the drill on a certain speed, you could create this diagram right here. And if you turn the speed up, you could create this diagram. And if you turn it up even more, then this diagram. But these waves that are created appear to be standing still, and they create these nodes. These nodes are at the ends of the rope where the wave appears not to move. So it appears not to move in that location and that location. This is what we call nodes. And if you turned it on faster and created this diagram, then there would be 3 nodes and then 4 nodes down here. But they also create antinodes where they have maximum displacement in the center. So this is a maximum displacement right at the maximum amplitude, this would have 2 nodes and 1 antinode. This would have 3 nodes and 2 antinodes. This would have 1, 2, 3, 4 nodes and 1, 2, 3 antinode. But these waves do appear to be standing still and are called standing waves. You will have a chance to mess with creating these in the interactive lab down below. Further increases in the frequency produce even more nodes and antinodes, such as these 2 diagrams. All right, waves in 2 dimension. Let's switch gears. We're going in 2 dimension now. Let's say we take this and we throw it into a pool of water. So that will create ripples in the water, and that's what we're calling 2 dimension. And we can draw those ripples. Those ripples can be represented by circles if we took a picture from the top, and they're called the wave front. And these are the lines that represent the crest of the waves in 2 dimension. These red lines represent the rays showing the direction the wave has traveled and are drawn at the right angle to the crest of the wave. So understanding how we can draw these, we can analyze them. We're going to look at 2 different scenarios. This first one is on a reflection of waves in 2 dimension. This is a wave generator that you can put a couple inches of water in and put your boundary, and this thing vibrates back and forth, creating a wave so that we can analyze the waves, how it reacts to the boundary. Well, drawing this picture would look like this. These lines here again would be the waves, crests, and the red lines would be the rays. Well, this ray that is coming in is called the incident ray. It hits the boundary and bounces off, creating the reflected ray. This line in the middle is called the normal line, and it is drawn perpendicular to the boundary. Now, the incident ray hits the boundary and creates an angle with this normal called the angle of incidence. This is the angle between the incident ray and the normal. And when the ray bounces off the boundary, creating this reflected ray, it also creates an angle called the angle of reflection. This is the angle between the reflected ray and the normal. And this law of reflection states that the angle of incidence is equal to the angle of reflection. This information could help you on a billiards ball table. Let's go to the refraction of waves. Yes, I said refraction, not the reflection. Refraction of waves in 2 dimension. So the refraction refers to one wave entering a new media. So in this case, this change in direction of waves at the boundary between 2 different media is known as refraction. Now, one thing we need to know about refraction, whenever a wave travels through one media to another media, the frequency of the wave remains the same. So what changes? If the frequency stays the same and the speed changes, that would be the velocity, then the wavelength would have to change. So if that changes, the velocity is going to change. Remember, the media determines the speed. So if it changes media, then it will be changing its speed. Also, the amplitude changes, but the direction may or may not change. So consider light. Light can be looked at as a wave, and whenever light changes from one media into another, it changes its direction. It also changes its speed, and that actually is what's going on here. If you consider the pencil, light is traveling from air into glass into water, and this pencil appears to be bent. But does it always change its direction, causing the bended pencil? Well, if we enter the new media at a 90-degree angle, it will not appear to bend, which means it did not change its direction. So that is why the direction changes unless it hits at 90 degrees. And that brings us to the summary page on wave behavior. Remember, speed of the wave is only affected by the medium, and the frequency remains the same when a wave crosses a boundary into a different media. Remember, the superposition talks about interference, and we had two types: constructive interference when the amplitudes increase, and destructive interference when they decrease. And that led us to the 2D wave drawings, where we could talk about reflection and refraction. Remember, the law of reflection states that the angle of incidence is equal to the angle of reflection, and refraction, where the wave bends when it changes media. So that's it, folks. Cowboy Joe out.